Don't be afraid to give up the good to go for the great. This is some great advice from Mr. John Davison Rockefeller, and I'm sure it was key to the pivotal role that he played as one of the most influential people that there's ever been in the oil industry. My name is Jim Latto, and I am the Technology Manager at Strohm. It is my pleasure to share with you some insights into thermoplastic composite pipe and how we are making the difference in the subsea pipeline industry. So what did Mr. Rockefeller mean when he said that we should not be afraid to give up the good and go for the great? He was talking about change. To the point, he was actually encouraging us to embrace change. But change does not happen on its own. There's always a trigger. A good example of a trigger for change can be what we call disruptive innovation. And it is a disruptive innovation that I am here to talk about. To begin, let us first consider a universal view of a product lifecycle. This curve is generic and can be applied to any product or system, from the simplest widget that is popular for a few months with our children, to a methodology for managing a global organization. The stages are all the same. First, there is the inception or development of an idea. From here, if it is successful, we then go through a stage of introduction. And over a period of time, we see a growth or adoption until eventually we reach a plateau of maturity. And then there is a dilemma. Every product life cycle has an inevitable milestone where a decision has to be made to either continue with that product or retire it. If we continue, there are options. We can allow it to naturally decline, or we can innovate, seeking incremental improvements that will keep us moving onwards and upwards, prolonging or extending the lifetime of our product. Our industry is full of great examples of innovative product iterations, but a disruptive innovation is one that provides a real step change in productivity, and these are rare. To illustrate, let's take this idea of a disruptive innovation and apply it a little closer to home. So consider the subsea pipeline industry. When we look at traditional subsea pipelines, there is a long and successful track record, beginning with rigid steel pipe. For many years, this was the product of choice for oil and gas transportation, and definitely the most prolific pipeline product used in our industry today. Our first major example of disruptive innovation was the unbonded flexible pipe. Pioneered over 50 years ago by Technip, this product built on the robustness of the metals technology already used in steel pipelines, and introduced polymers as non-structural layers in order to provide a conduit for the transported fluids. This decoupling brought many advantages, making the pipelines flexible, led to easier and quicker installation. Creating a polymer conduit to contain the bore fluids allowed us to select materials that could better withstand the extreme fluids that the pipeline had to transport. In its 50-year history, the unbonded flexible pipe has seen continuous innovation and improvement. There are many options in terms of material. For the metal components, you can choose from low-cost standard steels all the way up to highly specialized exotic alloys. The polymers used in unbonded flexible pipe have also seen continuous development. Materials used for the fluid barrier have been refined to the point that we now have options based on polyethylene, nylon, and of course PVDF that have been specifically formulated for use in our industry, giving the best balance between robustness and chemical compatibility, ensuring a long and safe service life. Much like the introduction of flexibles built on the development of the metals used in rigid pipelines, Thermoplastic Composite Pipe, or TCP, takes the experience we have with the robust and qualified high-performing oil-field polymers and opens up a new world of possibility. The introduction of TCP represents a step change in the subsea pipeline industry, and Strohm bring an approach to its development which has its roots in the most innovative companies of today. The starting point for TCP was to create a platform that took full advantage of the highly refined thermoplastic polymer systems used in unbonded flexibles. Combined with the expertise, design tools, materials technology, as well as the mindset used in the aircraft and space industries, this platform gives us endless possibilities to refine and optimize the capability of subsea pipelines, and allows us to move forwards on a trajectory that not only meets the needs of today, but has the capability to meet the needs of the future. These are not just words. The evidence speaks for itself. A little less than 10 years ago, and only a handful of years since the concept of using TCP for subsea pipelines was created, we successfully introduced our first commercial product line for subsea well intervention. As it is the nature of TCP platform to evolve, and in partnership with the early adopters amongst our client base, we quickly built on this success and moved into the development and introduction of jumpers and flow lines. Whilst this was going on, we also led the way in the creation of a new DNV-authored industry standard that would govern the design, qualification, and use of TCP. In the last 5 years, we have sold and installed many subsea jumpers and flow lines, all of which are qualified to this robust industry standard. And today, we are in a period of exponential growth that is set to continue for the foreseeable future. Strohm is already an established supplier of TCP in the subsea pipeline industry. We are extremely proud of our track record and have several successful product lines covering subsea well intervention, jumpers, and flow lines. Looking to the future, we are already on the cusp of introducing the next generation of TCP. After recent advances in the capability of our materials, design, and manufacturing technology, deepwater risers are the next major product line that is ready for introduction. We are also expanding our business, meeting our clients' needs in the energy and transition space with safe and efficient hydrogen transport, as well as pipelines for carbon capture. So what is TCP? Well, it's really very simple. We have a multi-layer construction, not unlike the traditional technology, except that it's a fully bonded structure which is based on a single thermoplastic material family that has been selected to provide the best performance for the target application. To be more specific, we have taken the specialized thermoplastic polymers developed as a fluid barrier in unbonded flexible pipes and given them the job of also maintaining the structural integrity. We do this by adding either glass or carbon fibers in such a way that we add strength to the material in precisely the location and direction where it's needed. And all of this is carried out in a single production facility, employing our proprietary manufacturing technology that melt fuses all of the layers to form one continuous reinforced cross-section to an exceptionally high level of quality. There are infinite possibilities to create tailor-made structures in this way, but in TCP we focus on a combination of several key aspects, namely the internal pressure requirement, the external pressure requirement, as well as the overall tensile properties required for installation and operation. The result is a pipe body structure that is lightweight, flexible, and completely corrosion-free throughout its lifetime. We even have a built-in solution for adding weight, often to aid on bottom stability, or in the case of a riser, stability in the water column. It is beneficial to add weight. With TCP, you also have the option of this weight coming from an additional coating layer, which is extruded onto the pipe at our facility. This eliminates the need to add time-consuming and expensive ancillary equipment. Our weight coating is fully bonded to the pipe structure and is therefore part of the product that is guaranteed by us to perform for its entire design life. We continue this straightforward approach with our end terminations. We have a simple system of wedges that close around a metallic stem that is inserted into the pipe. This creates a mechanical lock around the TCP and transfers all of the load into the end termination body, and subsequently a flange or connector of your choice. This stem also carries the sealing system, which utilizes elastomer seals that are in wide use in subsea, and these are also tailored or selected according to your specific application. A key benefit of this end termination method is that there is no secondary process of epoxy filling or welding needed, and this leads to a very quick turnaround of a few hours to terminate the pipe. The space and tooling requirement is also very small, meaning that the entire operation can be carried out on-site or offshore, giving a large degree of flexibility on how and where you use the pipe. If desired, we can even train your own technicians to carry out this part. The core of the product is based on proven and qualified oil-filled thermoplastic polymers. To date, we have 3 options depending on your application. Our primary product line, and the source of our excellent track record, is our polyethylene pipe, which uses glass fibers for the reinforcement. Fully qualified, in accordance with the DNV standard F119, it boasts a respectable top-end operating temperature of up to 65 C, and the maximum pressure, based on what we have supplied to date, of around 5,000 psi. With all of the benefits of polyethylene for mid-level applications, this is the workhorse of the TCP product line. For more specialized or onerous applications, we have 2 material options utilizing carbon fibers for reinforcement. These are intended for high pressure and deep water, but also extend our operating temperature window up to 80 degrees C for nylon and 120 degrees C for PVDF. While the carbon fiber provides exceptional structural properties, these materials have been specifically developed to cope with extreme conditions such as high CO2 content and sour service. All of our TCP products boast an extremely low gas permeability due to the bonded cross-section and the additional shielding provided by the inclusion of fibers, which take up approximately 50% of the volume in the composite section. Strohm don't just offer outstanding pipe. We bring you many benefits and provide value that makes TCP an outstanding solution. In the following slides, I will dive a little deeper into each aspect of the supply chain and give you real examples of where TCP can and will be your product of choice. Let's start with the engineering and manufacture. Our robust engineering and manufacturing is the platform from which we start. On the surface, this looks very straightforward, but go a level deeper and you'll find a complex system based on know-how and experience. Some of you may recognize the image in the middle as a representation of a neural network. I chose this image because the definition of a neural network is a series of algorithms that endeavor to recognize underlying relationships in data through a process that mimics the way the human brain operates. So in a sense, it learns. And that's what we do at Strohm. Everything we do, every result we get, has a practical purpose, and that is to feed back into our platform to ensure we are continuously learning and improving. And ultimately, that we are able to bring our customers more options and more value. A common way to view how our engineering process works is to consider this pyramid approach. At the very lowest level, we strive to fully understand each and every constituent part of the raw materials that we build into TCP. This isn't just for interest. Everything we learn is used to design and simulate the next level. We do this because to be thorough is one of the guiding principles to building up a true digital prototype. The polymer is the base level constituent, and we have carried out tens of thousands of tests on polymer coupons. Some tests are used to purely characterize the material and ensure that it meets our expectations, but the majority are to validate what we already have predicted using our analytical tools and models. Consider properties such as chemical aging and resistance to rapid gas decompression. Understanding these things and having the ability to accurately predict their effects are key to the safety of our product, so we feel it is essential that we pay close attention at the very beginning in order to account for them in the design later on. This approach continues upwards. When we combine the polymer and fiber into a composite tape, or when we add multiple tapes to make a laminate, we fully simulate and then rigorously validate the performance. We use engineering know-how and science to create accurate models that are then used as the inputs to our structural design tools. Because we build products that need to last many years in such extreme environments, we don't just look at the virgin material. All of the products in our portfolio need to be robust, and therefore during our qualification programs, we subject the materials to many years worth of accelerated physical and thermal aging. We expose them to the most severe chemical environments, and often we do both at the same time. Our PA12 material provides a good example of this level of rigor. Over the last 2 years with Evonik, we have accumulated test data from hundreds of millions of dynamic loading cycles and have subjected the material to aging tests which in real time add up to over 55 years. So that's the basics. The interesting part now is that we take all of this data, design a high performance pipe, and then run our digital prototypes to produce a performance prediction for a multitude of single and combined loading scenarios. And then of course we validate our predictions through full pipe testing. We call this representative pipe validation. This is still carried out on the full-scale TCP construction, but we use shorter, more cost-effective samples and isolate load cases in order to make sure that predicted performance is accurate, not just for the final design output, but every incremental step we take to get there. Finally, we reach what we call the full-scale pipe. As we have an extremely detailed map of the product performance by this point, we optimize this phase. Full-scale tests can be extremely time-consuming and expensive, so we select the most critical combined load cases and carry out a program of testing that brings everything together. As is the intention of the pyramid, we start off with the basics and spread the net wide to enhance our understanding and our ability to simulate the constituent parts of the TCP system. We then move upwards, focusing on the more complex composite components until we reach the full product construction. From there we continue the focus into real product performance, and then end with a demonstration that is as close to the real-life conditions that the product will encounter for service lives up to and beyond 30 years. All the way, we are continuously designing, predicting, and validating every step in what is possibly the most robust and safe process of design and qualification in our industry. The pyramid gives you an idea of the extent of our understanding and the rigorous approach we have to design a TCP. But what about your specific application? The first step in evaluating any application is the service fluid assessment. This assessment gives us some very clear answers to which of our materials is suitable for your application. Based on the combined knowledge of our subject matter experts, and of course the huge amount of data we obtain during qualification, we can quickly identify a solution that is fit for purpose. We focus on your operational requirements and then further refine the assessment into areas such as chemical compatibility, resistance to rapid gas decompression and swelling. We then consider the long-term utilization of our materials, and safety is built in with the DNV standard F119. We first fit the test data to curves and then calculate the regression. At this point we need to make sure that all points, including outliers, are taken into account and apply what is known as the lower confidence limit. Also, from here we apply a safety factor based on the type of service, and only then produce a curve that we can use for design. This safety factor is significant and is intended to ensure beyond any doubt that when a TCP is in service, you can fully rely on its performance and integrity for the full service life. The data population is also important. The benefit of generating high levels of data, not just during qualification, but data that is representative of the continuous material supply that we receive, is that we can add an additional element of safety by ensuring that at all times the performance we consider for our design is well within the limits set in our specifications. If any specific batch does not meet the requirement, then it is not used in your pipe. It is a similar story when we look at the pipe design itself. Safety and robustness are key to our success. So in addition to the safety built into our materials, we continue the theme into the design. Consider the chart shown. When we design a pipe, we also create a digital prototype. That prototype is then digitally tested, and the output is the predicted performance that we need to validate through physical testing. Of course, what happens in real life does not always match what happens on the screen, so we retest digitally, taking into account the upper and lower tolerances from every step of our pipe manufacturing and end fitting process. This gives us two curves that represent the best case geometry as well as the worst case geometry. These are translated into an upper acceptance limit on performance and also a lower acceptance limit. The real expected performance, given that the need for manufacturing tolerances can never be fully eliminated, is generally in the middle of these two curves. A pipe with an as-built performance that is anywhere in between these two curves is considered to be acceptable in terms of our qualification. However, to continue our mindset of safety and robustness, the safety factor and resulting design space is calculated always from the lower acceptance limit, ensuring that the pipe will always have a very high minimum safety factor, regardless of whether it is at the low end or high end of the acceptance limit. As mentioned, the real performance is expected to be in the middle of the upper and lower limit. To give an example, we recently made a carbon fiber PVDF pipe that had a 5 mm laminate thickness. That is, 5 mm made up the structural component that resists the internal pressure, external pressure, as well as the axial tension. Once we completed the pipe, we made a prediction for burst using the as-built geometry. And as expected, the prediction was almost exactly in the middle of the lower and upper acceptance limits. To give you an idea of the accuracy of our digital prototype, and bear in mind we had never physically made that particular design before, the burst pressure was 1,100 bar, and more importantly, within a few percent of the prediction. Confidence is key, as is safety, and when we consider the safety factor for this design, the burst pressure was more than 3 times the operating limit, making this an extremely capable and extremely safe pipe. Let's move on to manufacturing. Located in the port of Amsterdam, we have our state-of-the-art production facility. Alongside our in-house extrusion capabilities, we have 3 TCP production lines. 2 of these lines are for commercial work, and 1 is a development line. We have 2 sets of carousels, and then a whole range of storage reels. The entire facility is clean, compact, and above all efficient, with all of our engineering, test, and production teams co-located. It's also very easy to visit us, with just a short drive to Schiphol Airport. In each of our production lines, we have a series of tape winders, and then what we call melt fusion stations, or MFS. The polymer liner is made on our extrusion line and sent to a carousel for storage. When it's needed, it's fed through to our tape winders, where the composite tape is wound at a specific angle to give the desired properties. At this point, we're not too concerned about micron perfect tape placement, as the system is fully capable of dealing with gaps and overlaps within the individual tape layers. The key is the angle. From here, the tape is then fed into our MFS, where our proprietary system applies just the right amount of temperature and pressure to create a fully consolidated layer. This process is repeated over and over until we have reached the desired thickness of laminate to give the pipe the performance that it needs. We also have the freedom to change the angle within any individual layer in order to tailor the pipe cross-section properties for specific applications such as riser systems. Regardless of this change, the process remains exactly the same, and we arrive at the end with a fully bonded cross-section tailored to your need. But what about the quality? Consider zero porosity, defects, voids as 100% on a quality scale. In general, a composite structure is as near to perfect as it gets when it's at 97% or above. And actually, this is the number used for the structures of the aircraft that we all like to fly in. When we order our raw materials, we specify that it must be at 98%. Anything less than that can be rejected, and it's not used in our TCP. In reality though, our process of consolidation actually improves the material, and we are typically above 99.9% of the time. Of course, there is the possibility of foreign objects ruining our day and becoming inclusions in the pipe. The first and best defense against this is to make sure that our manufacturing procedures and equipment are second to none in terms of design, maintenance, and general cleanliness. In reality, our purpose-built factory is a clean facility, and every effort is made to ensure that there's little to no possibility of contaminating the pipe. We don't even allow flies through the door. In addition to this, we also have 100% visual inspection during manufacture. And at the end of every pipe, dozens of samples are taken and inspected under a microscope. For the unlikely event where something does make it through, we also have a certified repair procedure that we can carry out online. We simply pause production, address the affected area, and then carry on. As mentioned earlier, the key advantage of a composite structure is that by placing the fibers in the right direction at the right location, we have an incredibly fine level of control and can tailor its performance to any application. What this actually means is that for any tape layer throughout the composite laminate section, we dictate the specific angle at which we lay the tape. In its simplest form, we split this into two main categories, which we call our flowline layup and our riser layup. Generally, the flowline layup is for the static or quasi-static applications that do not require an enhanced tensile performance. In these designs, the tape angle that we use gives us a balance between the internal pressure resistance, the external pressure resistance, and the tensile capacity of the pipe. As this name suggests, this is an ideal layup for flow lines and is also used for jumpers. For risers, or indeed any pipe that requires high tensile capacity, we do things a little differently. Within the composite structure, we actually vary the tape lay angle significantly. This allows us to maintain the balance between internal and external pressure capacity, while adding more fibers in the axial direction to achieve the tensile capacity. As with any balance, if you offset one aspect, then there's a trade-off. In the case of adding more fibers in the axial direction, we increase the pipe stiffness, and this can lead to a larger minimum bending radius. Here is an example of a carbon fiber PVDF pipe at various points in our manufacturing process. We currently have several material options for the various layers, and from a supply chain continuity perspective, this is important. But we also have materials that are tailored to the two main categories mentioned. In terms of qualification status, we have finished the majority of the testing and validation for the polymer and tape materials in the flow line and jumper category. In fact, these qualification projects will be fully complete by the middle of this year. In terms of pipe level qualification and validation, we are currently in the middle of a project that will qualify the first carbon fiber PVDF TCP for high temperature and high pressure deep water jumper and flow line operations. For the riser system, we have several more options in terms of material. On the previous slide, I mentioned that using the riser layup leads to increased stiffness of the pipe and may lead to an increased MBR. This is not a problem because again it's all about balance. To counteract the trade-off between tensile strength and stiffness, and in partnership with our key material supplier, we have developed a higher performance tape option which gives us increased strength exactly where it's needed to reduce the MBR. The qualification for this material is already underway, and we have plans for the full riser system qualification in the very near future. Once any pipe is made in our facility, we also run a series of quality tests to ensure the product meets our high standards. These tests range from a detailed examination under a microscope to a demonstration of internal and external pressure capacity at full scale to ensure that we obtain the expected performance. We are often asked about the need for continuous automated inspection. And while continuous automated inspection is useful if you expect to encounter defects, we approach the assurance of quality from a more fundamental perspective. The best defense is a good offense. Now, I've described a TCP platform, and the core of that platform is to provide a product that has been designed and manufactured to an extremely high standard. And that standard is maintained throughout and validated at every step in the process. Even though this is the case, we take extra steps during our production process. You can never fully design out the risk of unexpected events. We ensure that our manufacturing facility is treated like a clean room. We 100% visually inspect the pipe during manufacture, and we record every piece of data relating to the parameters and stability of our manufacturing process. But the question is often still asked, what about the parts of the pipe that we can't see? It would not be a good idea for us to start cutting into the pipe in the middle, so we have developed a non-destructive examination capability to give peace of mind where it is requested. The example shown is using a digital X-ray method of inspection. This method has already been used extensively on our polyethylene products, but the image shown is a scan of our PVDF riser. As you can see, the images of the pipe cross-section are of a very high standard. Incidentally, the quality of our manufacturing is also of a very high standard, so there is not much to see. To show that it does actually work, I did manage to find an image where we captured a piece of the blue tape on the outside of the pipe. For continuous inspection during manufacturing, we have also carried out trials on moving pipe, and the equipment performed admirably and maintains a very high resolution even at the fastest of production speeds. We were so impressed with the capability of this equipment that we are now exploring plans to use it for offshore inspection. We are extremely proud of the fantastic work carried out by all of our partners, and of course our own teams, to have produced such a comprehensive and capable platform. There are many inputs and outputs to consider when we look at our TCP platform. And like any complex engineering, it takes years to learn and then to fully understand. This is where DNV come in. With DNV, we have a body of expertise on TCP, and they also act as a certification authority to give you the confidence and assurance that the pipe you are putting in the water is fit for purpose, robust, and above all safe. When the pipe leaves the factory, it also has an extremely comprehensive set of engineering and operational documents, as well as certificates from DNV. The section here on the left is the base level qualification and type approval. All of the years of hard work and data is compiled, checked, approved, and then certified. Because of this detailed certification, you can be sure that we have followed the standard and then evidenced every aspect of what we use in the design and production of the product. On top of this, we have the section on the right. This is where we bring together any application-specific elements. And in a similar fashion, this is also compiled, checked, approved, and then certified by DNV. Here is where we also deal with any client-specific testing and qualification needs. Should your application be even more onerous than we have already qualified, or if you simply need to carry out an additional test, we can always extend the qualification to meet your specific needs. Now we will cover the transport and installation aspects of TCP. TCP is designed to be lightweight. This optimization means you don't need extremely expensive lifting systems to move it around. You have many more options when it comes to transportation vessels, and importantly, we enable you to make significant reductions in the cost of transporting all over the globe. To use an example, the reels in the picture each contain 2 kilometers of pipe. and have an all-up weight of just 80 tons. Compare this to an equivalent unbonded flexible, and it represents a significant reduction in both pipe weight as well as the weight of steel needed to construct the reel that has to support it. This optimization affects everything from the cost of loading all the way to the sea fastening systems that need to be designed and constructed for transportation. To top it all off, we also have a 9-meter draft at our quay, meaning that there are not many transport vessels that can't get to us for a quick and easy pickup. Most of the equipment for transport and storage is also used for installation, and there are many installation methods to consider. Due to the lightweight nature of the product, preparing the pipe onshore and then towing it to the desired location is not a problem. When you need to take it further out, the usual spread of carousels, which can also be loaded off facility directly from our own storage carousels, are able to be used. We often deliver on a subsea pallet. These can be taken to the installation location and wet parked, meaning that at your convenience, you can place it in the field for storage and then simply come along at a later date, uncoil it, pull it into position and then connect. And finally, we have reels. These are available in many different sizes, depending on the product. We've all seen images like the one on the right depicting the different reel sizes available. A common question that I am asked is, due to the stiffness, does the composite pipe always need a carousel? And the answer is no. During design, we balance the performance requirements of the pipe with the required MBR for storage and installation. This means that we are able to tailor the design of individual sections and even the full pipe to the available vessels or methods for installation. Our 7.1-inch flow line shown in the bottom right has an MBR of just 3.5 meters. This means we can fit several kilometers on a lightweight and easily transportable reel. If you don't need a Strohm reel to optimize overall weight, a standard flexible reel will do just fine for the majority of our pipes. This flexibility allows us to create an optimized product that will deliver value in many areas. It's not just a world-class pipe, it is a world-class solution. There is in offshore construction a very wide breadth of vessel types for pipe installation, ranging from very large and capable deep-water pipe-lay and construction vessels to small, multi-purpose vessels that have a much lower specification. Vessel selection is a key factor, not only in cost and schedule, but planning and installation methodologies. The higher the specification, the higher the day rate and mobilization costs, and the range between the highest specification to the lowest can be as much as $300,000 a day at the top to $40,000 a day for the more modest option. Let's take another example from our 7.1-inch flow line. The vessel requirement for this pipe is also fairly modest. In fact, when you consider this requirement, the options available for installation are numerous, and often where a replacement pipe is needed, there is likely to be a suitable solution already in the field. That was the case for this project. The specification of the MPV already on station was more than acceptable for the safe and efficient installation of the pipe. Due to the lightweight nature of the TCP, the product lends itself to be installed using a horizontal lay system. This reduces the overall complexity and was a good fit for the installation vessel, which was already on a long-term charter by the operator. All we had to do was add the lay equipment, some wire rope for the OBS solution, and a banding station to bring it all together. A few days after setting off, the first 2 kilometers of pipe was already installed. During this project, we also had the opportunity to demonstrate the flexibility of our end terminations. With the pipe already pulled into the platform, it was secured vertically, and then our offshore support crew added the final touch by fully fitting and testing the end termination in situ. And finally, we come to the deepwater riser. The benefits of TCP are numerous for this application. The lightweight nature of the pipe eliminates the need for buoyancy. The high strength means that you can dramatically reduce the length and use free hanging catenary configurations. The combination of these two aspects lead to very fast installation times and significantly optimizes your vessel timings and cost. We have already seen that TCP can be installed by a wide range of vessels. For deep water risers, this is also true. Our high-performance carbon fiber PVDF tape for deep water risers allows a bending radius of just 7.5 meters to be achieved. This means that most flex-lay vessels can be used to install either horizontally or vertically with only minor modifications to their configuration. Reel-lay vessels, such as the 7 Navica pictured here, are also perfect for TCP. Designed to install both rigid and flexible pipelines, the large reel storage capacity allows us to take full advantage of our design platform, striking the best balance between minimum bending radius and tensile capacity. And the stern-mounted and tilted lay system also ensures that this MBR is easily maintained throughout. And that brings me to the end of this presentation. TCP is a step change for our industry and provides significant value throughout the chain. Using our detailed and robust platform, Strohm will continue to improve and advance this world-class subsea pipeline solution. Thank you for your time. Please reach out if you have any questions on the current TCP product lines or any of our future products.